Okay, I'm going to use the phet simulator of circuits to introduce the concept of series and parallel circuits. Today I'm just going to do a quick introduction to series circuits, and then I'll follow up with a tutorial that looks at the key concepts there and the equations that go with it. No new equations, it's all really just Ohm's law, but we just got to be careful how we apply it. So I'm going to build a series circuit and in the process show you what it means to build a series circuit. So we want more than one resistor. So I'm going to start with an ideal battery. I'm going to connect some wires. All right, and so I'm going to choose a resistor, and then I'm going to put it in this branch. I'm going to choose this resistance. By default it's 10 ohms. I'm going to leave it as 10 ohms. Okay, then I'm going to add another resistor here. I'm going to make this 20 ohms. That's probably a quicker way I can do that. Okay, I'm going to throw in an ammeter because I got to measure the current. I want to measure the current at some point. And if you recall, an ammeter must be connected in series with that. And then I'm going to complete the circuit. So before I complete the circuit, I'm going to add a third resistor in there. Whoops. All right, I can live with that. I'm going to make its resistance 30 ohms. All right, so actually I'll make it 40 ohms. Okay. And whoops. And I'm going to add a switch in there. Okay, so what made this a series circuit? Well, very simply, I have 1, 2, 3 components, and a series circuit is any circuit that has more than one component, and that component can be anything, not just a resistor. It could be a switch, it could be an ammeter, and other electronic devices. What makes this as a series circuit is there's one loop from the positive to negative. There's only one path to get around, and therefore you must pass through everything. If I were to break the path anywhere, in fact that's what the switch is doing, nothing happens. When I close the switch, now I complete the circuit and I should have a flow of charge. Not a big flow of charge because I have a lot of resistance. You might think I have a lot of resistance. Why? Perhaps because of all those resistors. So if I want to show if I want to get more flow of charge, let me crank it up to, let's say, 20 volts. Not that that really matters here. Okay, now here's the question. I've got 20 volts here and I've got a current of 0.29 amps right here, okay, at the bottom part of the circuit. So this is a question I want you to seriously ponder and give some thought. What is the current? If that's a current through here, what is the current through this guy here? This is the 10 ohm one. In fact, let me show values. Okay, so there's a 10, here's a 20, here's a 40 ohm resistors. If the current through the 20 ohm is 0.29, okay, what do we expect about the current through the 10 ohm, and what do we expect about the current through the 40 ohm? All right, so ponder that for a minute. Okay, so here's what I'm going to anticipate many of you, not necessarily all of you, would answer. You'd answer that the current through this one is roughly twice as much as this one. This has twice the resistance. This has this has half the resistance, so it's going to have twice the current. Also, this 40 ohm has twice the resistance of this, so it should have half the current. So let's check it out. So I'm going to cheat and use this little current meter. Okay, so I don't have to put the ammeter. If I want to move the ammeter around, I'd have to connect it and break apart the different connections and insert it, which is a pain. So again, this is, let's read it, 0.29 amps. That's what we said before. And if I move it here, voila, whoops, we get 0.29 amps. 0.29 amps. Okay, so maybe we didn't get what we expected, right? In fact, what this is suggesting, and if I put it anywhere, it's the same current. And in fact, that's one of the most important properties of a series circuit, is the current must be the same everywhere. And that's really just the law of conservation of charge. I can't have a certain charge coming into here and then having a different flow of charge coming out. and therefore entering here at a different value. It doesn't work like that. So I want you to be thinking then, well, wait a second, why doesn't Ohm's law seem to apply here? Why does this has a different resistance than this one, how can they have the same current? Right? The voltage is 20 volts for the entire circuit, so that doesn't seem to be changing. Well, it's a subtle reason. So let's check it out by getting our voltmeter out. So let me put the current meter away. Oh, actually, let me see one other thing. So when I said earlier the 0.29 amps was through this one, you might have thought, well, wait a second, how do I know it's not through this one? Right? If I put the ammeter here, it's not really clear which current we're measuring through which resistor. And that's really just a way of telling you that the current must be the same everywhere. In other words, the current coming out of the 40 is the same that's going into the 20. The current coming out of the 20 must be what the current that went in, therefore it's the same current that's going, the current coming out of the 20 must be the same going into the 10. So that can maybe conceptually help you understand why that must be. Okay, so let's look at the voltage. So we know we have a 20 volt potential set up due to the battery. Okay, and so I'm going to follow the charge against the counter. So I'm going to go conventional rather than electron charge. Okay, so let's see what happens, and this is mimicking a lab. If I put my voltmeter here and here, right, it's a 0 volt drop. In other words, this is at 20 volts. This is still at 20 volts because the wire has no resistance. I have an ideal wire here. And we learned in a previous lab, when current flows through a resistor, there's a drop in potential. So I want you to anticipate what will be the drop in potential, the difference between this spot and this spot when I put the black here. In the previous lab, it would have been 20 volts, but when we put it here, we see it's 2.86. In other words, it's a fraction of that 20. And then if I put it between here and, now I'm going to move it between here and here, I see that this is a 5.71. So I got 2.86, 5.71, that's about 8.5. And if I put it across this resistor, I see that the drop is 11.5 roughly. So if I take 11.5, add it to the 8.5, I get 20. So what I want you to see here, even if the numbers are a little bit unfriendly, is the drop in potential across the 40 ohms plus the drop in potential across the 20 ohm plus the drop in potential across the 10 ohm adds up to the total drop. So what happens is when we put resistors in series, each resistor acts like a small drop of the overall whole that comes from the battery. So we can understand now why Ohm's law actually does apply and gives the same current. The 10 ohm has a small resistance, but also has a small potential across it. So if I take that small potential divided by a small resistance, I get the same value as if I have a bigger potential divided by a bigger resistance. And I will be the same. I is V over R here, V over R here, V over R here. The R's are different, and so are the voltage drops. And that's an easy mistake to make, is to think the voltage across here, here, and here is going to be the same as the battery. It's not. So I'm just going to finish up with a little schematic that will help you visualize this. I've always found it helpful. So imagine a simple circuit, okay, as like a waterfall, a river. So I've got the high potential side, the positive side. So think of that. Let's go to Niagara Falls. We're on the, before we go over the falls. So water's flowing. And then it drops when it passes through a resistor. So in a circuit, when we go through a resistor, we get a drop in potential. I didn't want that. Okay, so we have a drop in potential when we pass a resistor, and we're now on the negative side. And then what happens is that the battery pumps it back up. So I go from negative, so we have this water flow. Okay, so if this is at 6 volts, and we know that the negative side is at 0 volts, there's a 6 volt drop between here and here. Okay, now what happens if we put another battery, or excuse me, another resistor? In fact, let's put 2 more resistors. Well, the situation changes in that our positive side is still 6 volts. Our negative side is still 0 volts, and so we have a 6 volt drop between them overall, but when I have 3 resistors, I'm going to get 3 drops, where each drop is a fraction of the whole. Okay, so I've got a small drop here. Let's say this is a 2-volt drop. Let's say this is a 2-volt drop, and let's say that's a 2-volt drop. Okay, so I get 6 volts overall. And notice if the water's flowing through each drop, I've got the same amount of water from each drop. It doesn't change. So think of water going over a waterfall in steps. The amount of water going through each step is the same. It's just how much drop they have. So that supports the idea of current being the same through each one, but the drops might be different. Now you might ask, why will it always be equal number of drops? And the answer is no. The only way this would be 2, 2, and 2 if these resistances were all the same. If instead I had a big drop, then a little drop, and then a moderate drop, that would correspond to a big resistance, a small resistance, and a moderate resistance, such that the voltage drop is simply equal to the current times the resistance. Since the current must be the same for all drops, a big resistance gives us a big voltage drop, and I really should call that delta V. Okay, so that's a series circuit in a nutshell. We'll summarize the key ideas and give you practice with the notes.